Hello everyone, welcome back. In this lecture, we are going to solve few numerical problems on preemptive SJF, or we also consider this algorithm as shortest remaining time first. This is very important algorithm from GATE or NET point of view. So let's solve few previous year questions of GATE exams. The very first question on your screen is this. Consider the following processes. So there are four processes are given with the arrival time and the length of the required CPU burst in milliseconds. The scheduling algorithm used is preemptive shortest remaining time first, and the question was asked in GATE 2016. So let's draw the Gantt chart quickly without wasting much of the time. You can draw the Gantt chart like this. So let's say now this is moment 0. So according to the arrival time, there is only P1 in the ready queue. So at 0, only P1 can be scheduled. So this P1 starts its execution and it can execute till 3 unit of time, because at 3 unit of time a process is arriving, and the process P2 is arriving. It will preempt the process which is executing, because this is one of the preemptive scheduling algorithm, right? So this is 3 moment. Now at this 3 moment, if I consider now P1 requesting, because already P1 consumed 3 unit of cycle, so it is requesting 7 cycles, CPU cycles, and P2 arrive, it is requesting 6. So based on this comparison, P2 is requesting less number of cycles as P1, so P2 will be scheduled here. And P2 can execute till 7 unit of time, because till 7 unit of time no other process is arriving. So let's say P2 is executing till 7 unit of time. So let's say this is 7. Now here, if you look at P2 has been executed for 4 cycles. So now P2 will be requesting 2 CPU cycles, and newly arrived process, that is P3, it is requesting only 1 cycle. Okay, so that means less number of cycle is being requested by P3, so P3 will be scheduled here, and P3 can be executed for only 1 cycle. So let's say here till 8 P3 will be executing, and P3 is done with its execution. So once the P3 is over, by 8 P4 has also arrived, but P4 is requesting for 3 cycles, but P2 is requesting less number of cycles, so P2 will be scheduled here. And now P2 can finish its lifetime, so P2 will execute after consuming 2 cycles. So by 10 P2 will be over. So P2 is also done. Now there are only 2 processes left in the ready queue, P1 and P4. P1 requesting 7 cycle and P4 requesting 3, so P4 will be scheduled here. And from 10 till 30, P4 will be executing. Okay, so P4 is also done. Now P1 is left only, so P1 will execute for remaining required 7 cycles. So 7 means 13 plus 7. It will give us 20. Okay. Now this question is asking the average turnaround time. So if we calculate the turnaround time for process 1, process 1 is the completion time minus arrival time. So completion time of process 1 is 20, because process 1 finishes its lifetime at 20, and process 1 arrives at 0 moment. So that means the turnaround time for process 1 is 20. Similarly, we can calculate the turnaround time for process 2. Process 2 finishes at 10 unit of time, and 2 was arrived at 3 unit of time. So that means TAT for process 2 is 7. Then you can calculate TAT for third process, or P3. P3 finishes its life at 8, and it was arrived at 7. So only 1 is the TAT for this, and the TAT for fourth process P4, it was finishing at 13 and it was arrived at 8. So that means 5. Now because here we need to calculate the average. So if you calculate average TAT, of the system, it will give us 20 plus 7 plus 1 plus 5 divided by 4. So it is 27 plus 6, that means 33 divided by 4, and it will give us 8.25. So the answer of this question will be 8.25. It was the numerical type question. Now let's solve the next question. The next question is from GATE 2014. An operating system uses shortest remaining time first scheduling algorithm for preemptive scheduling of processes. Consider the following set of processes. So it is given. Arrival time, burst time, and process IDs are given. The average waiting time in millisecond we need to find out. So here we need to calculate waiting time. Let's draw the Gantt chart. So if I draw the Gantt chart here like this, now at 0 moment there is only one process, that is P1 in the ready queue. So obviously P1 will be scheduled at 0 moment. So when the P1 will be scheduled, it will execute without any interrupt till 2 unit of CPU cycle. And at this moment P2 has arrived. So that means now P1 is requesting 10 cycles because 2 already has been consumed, and P2 is requesting only 4 cycles. So P2 will be scheduled here, and P2 will keep on executing till only one cycle, let's say 3, and 3 another process has been arrived. So at 3, if we consider, it is requesting 3 unit of CPU cycles. P3 has been arrived, it is requesting 6. So if we compare less cycles or shortest required CPU burst is of P2, so P2 will be scheduled again, and P2 will continue for next 3 cycles. So it will finish its lifetime, let's say by 6, right? Now at 6 no other process has been arrived, so there is only 2 processes. P2 has been finished its lifetime, so P1 and P3 are there. P1 is requesting 10, P3 is requesting 6, so P3 will be scheduled here. Now when P3 will execute for 2 cycles, machine cycle, P4 arrived. So now P3 has been consumed 2 cycles, that means it is requesting for 4 cycles, and the newly arrived process requesting 5 cycles, and P1 is requesting 10 cycles. So that means P3 will continue, and P3 will consume required 4 cycles, so it will finish by 12, right? Now once this P3 has been finished, then P4 will be scheduled. So P4 will be scheduled and it will consume the required 5 cycles here. So till 17 P4 will finish, and now P1 will consume remaining cycles. So P1 is requesting for 10 more cycles, it will finish, let's say till 27. Okay, so this will be the Gantt chart. Now if you want to calculate the waiting time, so let's calculate waiting time for process 1. Waiting time is, it is n number of ways we can calculate the waiting time. So because it is preemptive scheduling, there will be multiple waiting rather than single waiting. So let's say consider for P1, initially P1 arrived at 0 and scheduled at 0. So it has been started execution at 0 and arrived at 0. So 0 minus 0, it is the very first waiting. But you focus here, P1 is stopped here or preempted here, and P1 again started here. So this is also the another waiting time you consider, like, so 17 minus 2 we need to add in the waiting time. So let's add it. So the second waiting you can say 17 minus 2, because at this moment the process was again added to the ready queue and it's again start executing at 17, right? So overall waiting of process 1 will be 0 minus 0 means 0, 17 minus 2 means 15. Now calculate the waiting time for process 2. So the process 2 starts at 2 and arrived at 2. So initially there is no waiting. and it is keep on executing and finish this lifetime. So that means 0 waiting for process 2. Now for process 3, the waiting time, if you calculate, process 3 starts at 6 and process 3 arrived at 3, right? So process 3 was arrived at 3 and process 3 start executing by 6 moment, and then it is finishing its lifetime by 12 in between, so no switching in between. So the total waiting is 3 for process 3. Now calculate waiting time for process 4. Process 4, the waiting time for process 4 starts executing by 12 and it has been arrived by 8, and there is only single waiting. Process 4 is finishing its lifetime here only, so it is 8. If we want to calculate the average waiting time of the system, it will give us 15 plus 0 plus 3 plus 8. So altogether it is 26 divided by 4, and that means 6.5. Okay, so 6.5 will be the average waiting time for this, so answer will be D. Okay, now let's solve the next question. The next question is from GATE 2007. An operating system uses shortest remaining time first process scheduling algorithm. Consider the arrival time and execution time for the following processes. Processes are given. Total waiting time for the process P2. So we need to calculate just the waiting time for process P2. So let's quickly draw the Gantt chart. Now let's consider this is the Gantt chart. So okay, so this is 0 moment. Now at 0 only P1 is in the ready queue, so P1 will be scheduled. Okay, and it will keep on executing till 15 machine cycle. So till then no other process is arriving to ready queue. So let's say I assume that this is 15 or maybe some lesser length. So let's say assume that this is 15. Okay, now here when it at 15, before 15 actually, at time, or you can say unit of 10 unit of time, P3 was arrived. When P3 arrived at 10, there's a conflict. So let's decide before that. So let's say P1 start executing. P1 is executing till 10 smoothly. There is no interrupt. But at 10, I am assuming this is 10. P3 arrives in. No, this is not the arrival time, guys. Arrival time is here, so don't get confused. 0 moment, P1 is scheduled. Okay. Until 15, no other process is arriving. So P1 will execute till 15. So I assume that this is 15. Okay. Right. Now P2 arrived here. When the P2 is arrived in the ready queue, then P1 only requesting 5 unit of CPU cycle. So that means P1 is requesting less as compared to P2. Okay. So P1 will continue and P1 will continue till 20. Now P1 is done with its execution. It is finished, right? Now no other new process has been arrived. In the ready queue only P2 is there. So P2 will be scheduled here. Now P2 will execute till 30 because no other process is there to interrupt. So from 20 till 30, let's say P2 is executing. Now at 30, P3 arrived. But what are the cycles requested by P2 at this moment? 30. So it has already consumed 10 unit of cycle. So it is requesting 15 now. And P3 is requesting 10 only. So that means at 30, P3 will be scheduled. Now when P3 start executing from 30, it can execute till it is requesting 10, so 40, because at 45 new processes arriving, so it is smoothly executing till 40. So let's say I assume that this is 40. Now at 40 this process has been finished. P1 we have already finished, right? So P3 has been finished, but P4 doesn't arrive. That means P2 will be scheduled again. And P2 was requesting 15 cycles, so it will execute for more 5 cycles till 45. And at 45 this P4 has arrived. So this time the P2 is requesting only for remaining 10 cycles, and P4, which is arrived just now, it is requesting for 15 cycles. So that means P2 will continue for 10 more cycles. So P2 will continue, let's say, and this is 10 more, so 55 cycles. And now P4 will be scheduled. So P4 will be scheduled now, and P4 is requesting 15 cycles. So from 55 till, let's say, 70, it will be executing, right? So this is the Gantt chart for this particular scenario by utilizing shortest remaining time first or primitive SJF, right? So let's calculate the waiting time for process P2. The waiting time for process P2, if we want to calculate, so I am writing waiting time for process P2. P2 starts here at 20 and P2 arrived at 15. So this is the very first waiting time plus P2 interrupted at this moment 30 and P2 again started at 40. So second waiting is 40 minus 30. There is no third waiting for P2. So altogether it is 5 plus 10 is equal to 15. So the answer for this question will be 15. Okay. I hope it is clear. Now let's move on to the next problem. Which of the following statements are true? It was asked in GATE 2010. So the very first statement, shortest remaining time first scheduling may cause starvation. Shortest remaining time scheduling can cause starvation. You assume that if there are processes arriving, let's say P1 arrived in the ready queue, let's say P2 arrived in ready queue, P3 arrived in ready queue. There may be the situation, let's say one of the process is requesting very large amount of cycle, large CPU burst required or cycles. And if again and again the processes are coming in the ready queue, those are requesting less number of CPU cycle, then this P3 must be waiting for a very long period of time to get the CPU control switched. That means there are chances, considerable chances to get the starvation kind of situation, right? So the very first statement is okay, it is true, no problem in that. Second one, preemptive scheduling may cause starvation. Yes, preemptive scheduling can cause starvation. There are different types of preemptive scheduling. So maybe preemptive priority, if I consider in preemptive priority scheduling, the similar kind of situation can occur. If there are more than one processes are waiting in ready queue and other processes are keep on coming in the ready queue. Let's say if I consider P3's process priority is very less, and whatever the processes are arriving in the ready queue again and again, they are having the higher priority. Then this P3 can be stopped, right? If you are utilizing, let's say, preemptive shortest job first, let's say you are not incorporating this, let's say you are incorporating preemptive SJF, then also a process can be stopped if again and again the smaller CPU request processes arriving in the ready queue. As I have discussed, a process which is requesting large amount of CPU burst can be stopped or need to be in the ready queue for a very long period of time, right? So second also we can say it is true. So this is true statement. This also true. Now look at the third one. Round robin is better than FCFS in terms of response time. So what is the response time? Response time when a process is in the ready queue and waiting for the CPU to be switched or allocated. That is the response time. Okay. If a priority, or you can say if a scheduling is non-preemptive, then the waiting time is equal to response time, right? So if we compare round robin as compared to first come first serve, round robin try to allocate CPU uniformly, equally to all the processes. So it balances the response time of the system. In that way, we can say round robin is better than first come first serve. So this statement also you can consider as true, right? So that means if we look at the answer should be D, where all these statements are correct. Okay. So please do remember preemptive SJF or shortest remaining time first. Scheduling is same, and I hope these example will help you to understand this particular algorithm. Thank you everyone. So I'm closing this session. See you in the next session.